The paper I'm presenting is self-supervised pre-training of spin transformers for 3D medical image analysis. So this the authors are mainly from NVIDIA, and two are from Vanderbilt University, uh, Yucheng Tang and Ali. But during the time when they present this, when they present this paper, like Yucheng was working for NVIDIA as well as an intern or something. So, so the contents of this paper, I break the presentation into several sections, mainly introduction, related work and problem, proposed work. This is the brief method, and then the method in detail, pre-training, experiments, conclusion, strengths, weakness, and future direction. So we all know why medical image computing is important. So I'm not going to waste a lot of time on this topic. So medical image computing has like a lot of uses. So uh, enable doctors accurately diagnose and treat medical conditions by analyzing medical images, provide better understanding of various medical conditions. Medical professionals can detect diseases at early age. So, personalized treatment, improved surgical planning, drug development. There are many uses. So, related work and problem. So, in the past, medical image computing is dominated by CNN-based architectures. So then we all know the vision transformer came, and vision transformers are revolutionizing the computer vision and medical image analysis. So the transformers are effective at learning pretext tasks, global and local information, and are scalable at large scale training. So like unlike CNN, which focus on local, transformers are good at local and global both. So VIT encode visual representations from sequence of patches and leverage self-attention blocks and modeling long-range global information. Then the famous SWIN came. Shifted windows transformers propose a hierarchical VIT that allows for local computing for self-attention with non-overlapping windows, making it more efficient. So we know that VIT was not good at segmentation tasks because it could not catch the lower level. Very small resolution. But this is SWIN was a very SWIN was able to overcome the weakness of VIT. So transformer-based models perform favorably on fine-tuning downstream tasks compared to CNN-based counterpart. Medical image analysis has not fully benefited from these advances due to large domain gaps and lack of cross-plane contextual information. So medical image analysis is an important field that presents many challenges due to complexity and variability of medical images. Existing models often require large amount of labeled data to train effectively, which can be difficult because even for the labeling, there should be experts, and those experts are expensive. So SWIN transformer have shown some promise in image analysis tasks, but they require large amount of labeled data. So we know that. So self-supervised pre-training is a technique that allows a model to learn useful representations from a data without requiring labeled data. This is a key. So proposed work. So this is the paper in brief. The authors propose a method for self-supervised pre-training of SWIN transformers for 3D medical image analysis. Method involves training SWIN transformer on a large unlabeled dataset of 3D medical images using self-supervised objective function that encourage the model to learn useful features. The authors evaluate their pre-trained model on several medical image analysis, show it outperforms state-of-the-art methods. The proposed method has the potential to improve the accuracy and efficiency on medical image analysis. So now we talk about the method in detail. So this is a transformer-based architecture. So it has a SWIN encoder, directly utilize 3D patches, and then connected to a CN-based decoder. So this is the overview of the architecture. We see that this thing has 4 layers. Each layer has 2 transformer blocks, so we have eight altogether. So they send patches, and then like in the swing, like that they have the patches, and they reduce the resolution, and then the I mean this model is like so then finally we have a segmentation ahead. So the key is like the shifted window mechanism. So they compute the attention in windows, and then to get the global information they shift the window like this, and then they compute the self attention. So they have the image has the idea of what is going on in the later outside of their window as well. So the encoder takes 3D subvolume. It creates sequences of 3D tokens projected into C-dimensional space via an embedding layer. The input volumes are partitioned into non-overlapping windows. Local self-attention is computed within each region for efficient modeling of token interactions. So encoder consists of 4 stages, as I said, with 2 transformer blocks at each stage. Patch merging layers are used to reduce the resolution by a factor of 2 between every stage. This is common in swing. The hierarchical representations of the encoder at different stages are used for downstream applications such as segmentation for multi-scale feature extraction. So if you look at the like swing transformer block, so we have the signal Z I minus 1. So then it goes through a layer normalization, linear norm, and window multi head attention, and then they have this skip signal, and then it is going through Z hat, is going to the linear norm again, multi-layer perception, and this signal comes again, and then this we say ZL, and ZL is going through again linear norm and shifted window multi-head attention. Okay, here we take the global information, and then again skip. So then it continues. So attention mechanism, queries, keys, and values, it's same as before. Encoder use patch size 2 by 2 by 2, feature dimension 2 by 2 by times 1 equals 8 for single input channel CT images. Encoder has 48 dimensional embedding space and 4 stages with 2 transformer blocks at each stage. Patch merging layer used between stages to reduce resolution by factor 2. Linear layer used to downsample resolution in a stage 1 by reducing dimension by 2. Same procedure continues in stages 2 and 4 with resolution first h over 2, and then h over 4, then h over 8, and h over 16, so respectively. So decoder is a connected to a CNN-based decoder. Encoder is connected to a CNN-based decoder at each resolution via skip connections. Output sequence representations from each stage and the bottleneck are extracted and reshaped into features. Process features are sampled and concatenated with the features of the preceding stage. For segmentation, the encoder's output is concatenated with process input features. The concatenated features are passed through a residual block, and a final convolution layer is to compute probabilities. So now we talk about pre-training. So the pre-training, so Swin UNETR encoder is pre-trained with multiple proxy tasks such as mask volume in painting, image rotation task, contrastive coding. So 3D tokens. So 3 additional projection heads are attached to the encoder during pre-training, and so they compose a loss function that consists of all these 3 proxy tasks. So something like this, and so with the previous one, mask volume in painting. If I talk about mask volume in painting, so region of interest in the subvolumes are X are randomly masked out using cutout augmentation and transpose convolution layer is attached to the encoder for reconstruction. So the image rotations, multi-layer perception classification head is used for predict angle categories. Cross entropy loss is is used for rotation prediction. Then the contrastive coding, a linear layer is attached to the SWIN UNETR encoder to map each augmented subvolume to latent representation. So they use cosine similarity, is used for distance measurement. Contrastive coding is loss is maximizing mutual information between positive pairs and minimize between the negative pair. So this is the idea of it. And then we have overall loss function. So they have their experiments. They use data sets, pre-training data sets, 5 publicity data sets, so 50 subjects, 3D volumes for chest, abdomen, and head and neck, and then they use BTCV data set, and they have like SMST data set. So training details, they use Adam optimizer with warm-up cosine scheduler with 500 iterations, batch size 4 per GPU with 9696 batch. Initial learning rate is this, momentum is this, and decay rate is this for 450K iterations. Implemented in PyTorch and Mon A14. 5-fold cross-validation strategies used for BTCV and MSD experiments. Best model selected in each fold and ensemble their outputs for final segmentation predictions. So now, we look at the results. So this is BTCV multi-organ segmentation challenge. So we see that the models SWIN UNETR achieved state-of-the-art results. So the spleen, they have spleen, right kidney, left kidney. Left kidney we do not have state-of-the-art, but like most of the organs, they have state-of-the-art results. So proposed SWIN model is compared with baselines like other models. SWIN UNTR achieves best performance with dice of 0.9. Okay, they use dice, for their metrics. So performance with dice is 0.908, outperform the top rank baselines by 1.6% to 2.4% on average with 13 organs. SWIN UNETR detect pancreas, tail, and branches in the portal vein where the other methods fail. SWIN UNETR also shows distinct improvement in segmentation of adrenal glands. So this is a visualization of proposed SWIN UNETR and baseline methods. So we have like different baseline methods. So then this is another the paper present MSD segmentation task. So segmentation results on MSD. So SWIN UNETR achieves state-of-the-art performance in several tasks here, not like the previous one. And best average of DICE 78%, 68 across all 10 tasks and top ranking in the leaderboard. Pre-trained weights using for fine-tuning CT tasks, trained from scratch for MRI task. So these are the qualitative results of representative MSD CT task. So average DICE values are illustrated in the top of the image. So these are the DICE values. So then the paper did some ablation study, and we see that so they were able to improve DICE with when they take like different proxy task, like instead of they take rotation, they have like 83. Then they combine like in paint and rotation, they have 84, and in paint contrast and rotation, they've significantly improved the performance. So then again, like here they use pre-training. So when they use pre-training, we see that the dice score also improves. So they have these pre-training things. The paper did some analysis on that. So they have the paper nicely discuss about it. Data efficient performance on BET, CV test data set when they have like pre-training. So it increases the performance. Dice score, it increases. So the conclusion. So this paper solves significant challenge, because previously, they addressed the lack of unlabeled data. So this is a good paper. Author proposed a method for self-supervised pre-training of swing transformers for 3D medical image analysis. Method involves training the swing transformer on a large unlabeled data set of 3D images using self-supervised objective function that encourage the model to learn the useful features. Paper achieved state-of-the-art results. What matters. So this is, I would say, this is a 4-star paper, very good paper. The strengths: paper managed to overcome limited availability of labeled data sets. The biggest issue: the introduced self-supervised pre-training approach allows for the use of unlabeled data. Paper gives us detailed explanations. Paper uses 2 different medical image analysis tasks. This demonstrated the generalizability of the method in different type of tasks and data sets. So the results show that pre-training with the self-supervised tasks highly improve the performance on both tasks, even when the pre-training data is from different modality than the task data. The paper compare the introduced approach with other pre-training methods. The paper provides a thorough analysis of the learned features and their use of downstream tasks, which help to explain why the self-supervised pre-training approach is effective. The paper includes detailed experiments and ablation studies to demonstrate the effectiveness of their different components for the proposed approach. The paper presents new use of swing transformers for medical image analysis and demonstrate their potential for improving performance on variety of tasks. So the weaknesses of this paper: the paper only evaluate the method on 2 medical image analysis tasks. So they could have done this into different tasks. It is unclear how well the method would perform on other type of data sets. The paper does not provide a detailed comparison test of the computational requirements of the method. The paper does not provide a detailed analysis of the limitations of proposed approach. The predictive, these can be the future research potential. The predicting the relative position of image patterns, which may not be the most effective task for learning useful features for type of medical image analysis task. The paper does not provide detailed analysis of the failure cases of this method. So paper assume to access to large amount of unlabeled data for pre-training, which may not always be available in real time. This is one of the biggest shortcomings of my paper, because this is a good paper, but in practical we have some issues. The paper does not compare the method to the other state-of-the-art methods on the evaluated task. So future directions, I would say exploring other self-supervised pre-training tasks, evaluating the proposed approach on more different medical image analysis tasks, analyzing the limitations of the method, comparing the method to other state-of-the-art methods, scaling up the method on a larger data sets. So this is my presentation, and I really like the paper. And thank you.